Welcome to Sleepy Harbour. Settle in. Let the lamp be low, let the pillow take the weight of your head, and let the day you have been carrying slide, slowly, off your shoulders and onto the floor where it can wait until morning. There is nothing left tonight that needs your hands, nothing that needs deciding. You are here, and here is quiet. And the only thing asked of you for the next little while is to listen, and to drift, and to let a life much older than this evening carry you gently down into sleep. Here is something to hold as you go under. By the time she was 25 years old, Rosalind Franklin had already made her name as a scientist. She was respected. She had published work that other researchers would go on citing for decades, work that would find its way into the foundations of whole fields, and she had never, in all of that, touched DNA. Not once. Not the molecule, not the photographs, not the argument that would one day swallow her memory whole. The story most people know about her had not begun yet, and would not begin for years. And by then the woman at the centre of it was already an accomplished person with a completed piece of first-rate science behind her, done with helium and coal in a quiet laboratory outside London during a war. That is the strange thing about the way we remember her. If you have heard of Rosalind Franklin at all, you have probably heard her in one shape only. The wronged woman of Newnham, the photograph taken without her. The prize she never got. And all of that is true, and we will walk through every part of it tonight, slowly and honestly, the way the record actually supports, rather than the way the legend has swollen it. But that single story, repeated so many times it has worn a groove, has quietly become the whole of her. And a life reduced to the worst thing that was done to it is a life erased a second time, more gently than the first, but erased all the same. So tonight we are going to do the slower thing. We are going to meet the scientist before we meet the grievance. We are going to give her back the shape of a full life. Wherever you are listening from tonight, I would like to know. Leave a word in the comments and tell me what part of the world is dark outside your window right now. What city or what quiet stretch of countryside is holding you while you fall asleep? It is a small thing, but it makes this harbour feel less lonely, and I read them. If you are new here and you would like more slow stories of this careful kind, the ones built to walk you down into rest rather than jolt you awake, you can subscribe and stay a while. And now, let us begin where she began, a long time ago, on a summer day in London. She was born on the 25th of July, 1920, in Notting Hill, in the west of London, into a family that was not merely comfortable, but genuinely eminent. She was the second of 5 children, and the family she arrived into was Anglo-Jewish, prosperous, cultured, and steeped in a tradition of public service so deep it was less a habit than an expectation. To be a Franklin in that house was to be someone who would do something with your life that mattered to more people than yourself. The only question, unspoken but always present, was what shape that something would take. Her father was Ellis Arthur Franklin, a merchant banker, part of the banking house of Keysers, a man who moved through the world of finance by day and yet was not content to let that be the whole of him. In the evenings he taught. He gave his time, without pay, at the Working Men's College, standing in front of ordinary labouring men and explaining to them the mysteries of electricity and magnetism, the invisible forces that make a compass swing and a wire hum, and he taught them, too, the history of the Great War, the vast and terrible thing that had ended only 2 years before Rosalind was born, and whose shadow still lay, long across every English family. Picture him there in the lamplit evening room, a banker teaching physics to men who worked with their hands, believing plainly, that knowledge was a thing you owed to other people and not a thing you hoarded. That was the water she swam in. That was the family temperature. And it went back further and reached higher than one thoughtful father. Her great-uncle was Herbert Samuel, and Herbert Samuel was not a minor figure. He was the first practicing Jew ever to sit in the British cabinet, at a time when that was a genuine barrier and not a formality, and he would later go on to serve as the High Commissioner for Palestine, a man whose name appears in the ordinary history books of the century. So when a Franklin child looked up at the adults around the dinner table, she did not see people who wondered whether one might amount to something. She saw people who already had. The bar was not encouragement. The bar was assumption. And it was not only the men. There was her aunt, Helen Caroline Franklin, known within the family as Mamie, and Helen was her own kind of force. She was active in the movement for women's suffrage, in the long, unglamorous, often dangerous fight to win women the vote. And she was active, too, in trade unionism, in the organizing of working people to bargain for their own dignity. So the young Rosalind grew up not only among achievement, but among a particular idea of what a woman might do with a strong will and a sharp mind. She grew up understanding, from the inside of her own family, that a woman could stand in a public square and demand that the world change, and could sometimes, slowly, make it. Hold that picture for a moment, because it matters for everything that comes after. The story we usually tell about a woman going into science in the 1930s and 40s is a story of a lone girl with no support, pushing against a family that wanted her married and quiet. That is not quite Rosalind Franklin's story, and the difference is worth resting on. Hers was a family that expected greatness. What it did not expect, what it did not have a shelf ready for, was greatness of this particular kind. A Franklin might reasonably become a great lawyer, a great banker, a great reformer of society, a servant of the public good in a courtroom or a committee or a charitable board. Those were the honoured roads. The laboratory was not on the map. And so the friction she met at home was not the crude thing of a father who saw no worth in his daughter. It was subtler, and in some ways harder, because it came dressed as love and reason. Because there is a story that gets told about Ellis Franklin that he flatly refused to pay for his daughter's scientific education, that he shut the door on her. And the honest version, the one the careful biographers have settled on, is softer and more human than that. He was ambivalent, he was uneasy about university for women in general, uncertain that it was the right path, and if he had had his way, he would have preferred that she pour her considerable energy into social work, into the kind of visible good in the world that the family understood and prized. There was real friction between them over this. There were hard conversations and disapproval that she could feel. But there was no absolute wall of money slammed down. She went. The family's means and the support of that suffragist aunt, among others, were part of how she went. So set aside the melodrama of the tyrant father and keep instead the truer, quieter thing. A girl determined to do a kind of work her family did not fully understand, pushing not against contempt, but against a gentler, more bewildering current of concern. That is a harder thing to push against in some ways, because you cannot simply be angry at it. You have to keep loving the people who keep asking whether you are sure. And she was sure. That is the remarkable part. She seems to have been sure very early. She was sent to St. Paul's Girls' School in London, and this was itself a piece of unusual good fortune, because St. Paul's was one of the very few girls' schools in the whole city that taught physics and chemistry to a serious, high level. You have to understand how rare that was. In most schools for girls in that era, the sciences, if they were taught at all, were taught lightly, as a kind of ornament, an accomplishment rather than a discipline. The assumption, everywhere, was that a girl's mind either could not or need not go into the hard, exact places where physics lives. St. Paul's did not assume that. St. Paul's put real chemistry and real physics in front of its girls and let them find out for themselves whether they could do it. And Rosalind Franklin could do it. She excelled there, and not only in the sciences. She was good at sport as well, a physical, energetic child who liked to move as much as she liked to think, and that combination, the athlete and the analyst in one person, would stay with her all her life. And it was there, at that school, at around the age of 15, that she is said to have announced her intention. 15. Think of where you were at 15, of how unformed most of us still are at that age, how much we are still trying on selves like coats to see which one fits. And this girl, in a family that would have handed her a dozen respectable futures, looked at all of them and said, plainly, that she was going to be a scientist. Not a hope, not a maybe, a decision made early and held. There is something almost startling about that steadiness in a 15-year-old, and it tells you the most important thing you can know about the woman she became. She was not, at any point, a person who drifted into things. She chose, and having chosen, she did not waver, and she did the work. Let that settle over you as you lie there in the dark. A young girl in 1930s London, in a school that was one of the only ones that would teach her what she wanted to know. Deciding at 15 exactly who she meant to be, and then simply refusing, over years and against friction, to become anything else. From St. Paul's, the path led, as such paths did for the brightest, toward Cambridge. And in 1938 she went up to Newnham College, one of the colleges at the University of Cambridge that admitted women, to read natural sciences. She was 18 years old, and she was walking into one of the oldest and most storied centres of learning in the world, into stone courtyards and libraries older than nations, into the very heart of English science. And she was walking into it, we should be clear, as a kind of half-citizen. Because here we meet the first of the structural injustices in her story, and it is worth pausing on precisely because it happened years before Dna, before any photograph, before any single man could be blamed. It was built into the institution itself. At that time, the University of Cambridge did not grant women full degrees. Let that sink in for a moment, because it is easy to hear and hard to actually believe. A woman could go to Cambridge, she could sit in the lectures, she could do the laboratory work, hour after hour, exactly as the men did. She could take the same examinations, be tested on the same material, be judged against the same standard. And she could pass. She could pass brilliantly. And at the end of all of it, she was awarded what was called a titular degree. A degree in title only, the name of the thing without the substance of it. She had, on paper, done everything a Bachelor of Arts had done, and she was not made a Bachelor of Arts. She was given, in effect, a certificate that said she had earned a degree, while the degree itself, the full and recognized standing, was withheld. Imagine sitting an examination that the man beside you is also sitting, answering the same questions, perhaps answering them better, and knowing that when the results come back, his will be a degree, and yours will be a shadow of one, a courtesy, a token. And this was not some ancient policy on its way out. The University of Cambridge did not begin awarding women full degrees until 1948. Rosalind Franklin earned her degree qualification in 1941, 7 years before the rule changed. So she is one of the women who did all the work of a Cambridge scientist and was handed, at the end, the polite fiction of a degree rather than the real one. I want you to hold that fact gently, because it does something important to the shape of the whole story you are going to hear tonight. When people tell the tale of Rosalind Franklin, they very often make the injustice personal and singular. They make it about one photograph and a small number of men, as though but for those particular men, the world would have been fair to her. And the truth the record shows is larger and quieter and sadder than that. The unfairness was in the machinery long before she reached the part of her life that made her famous. It was in the very degree she was not quite given. It was institutional, structural, woven into the stone. The pattern that would show itself so painfully later was not an accident of a few personalities. It was the water she had been swimming in since she was 18 years old, walking into Cambridge as a person the university had already decided to hold slightly apart. And Cambridge, for all its beauty, was not simply kind to her in those years. The graduate year that followed her undergraduate work, the year meant to launch her into research, was an unhappy one. She spent it working under a physical chemist named Ronald Norrish, a man who would himself, much later, win a Nobel Prize, a figure of real standing in the field, and the two of them did not fit. They clashed. Franklin found him obstinate, immovable, a person she could not work with in the way that good research demands, where the older scientist opens doors and the younger one runs through them. Instead, there was friction and stubbornness meeting stubbornness, because she was not a person to soften herself to fit a difficult superior, and he was not a person inclined to bend toward a young woman who would not defer. We should be fair here, and being fair is part of what we are doing tonight, part of the slow honesty this story deserves. It is easy from a distance to make Norrish a villain, one more obstacle in a line of men who failed her. But the more careful reading is simply that it was a bad match, a poor pairing of two rigid temperaments, the kind of thing that happens in laboratories and workplaces everywhere and always. What matters for our purposes is what it revealed about her, and what it set in motion. It revealed that she needed the right conditions to do her best work, that she did not flourish under a supervisor who fought her rather than freed her, and that she would rather leave an unhappy situation than shrink herself to survive inside it. And that is exactly what she was about to do. Because a war was on. It was 1941, 1942. And Britain was in the middle of the Second World War, and the whole country had been bent to the single purpose of survival. In such a time, an unhappy fellowship studying pure chemistry in a Cambridge college could come to feel like a small and distant thing, a private discontent against the enormous fact of a nation at war. And Rosalind Franklin, restless in her graduate year, unhappy under Norrish, and possessed of that early, hard 15-year-old certainty about who she was meant to be, made a decision. She would leave. She would set aside the fellowship, the safe and prestigious Cambridge track, and she would go and do work that was useful in the immediate, practical, wartime sense, work that touched the actual struggle the country was in. And so, in 1942, she took a post at a place with one of those wonderfully plain, functional British names of the period. The British Coal Utilisation Research Association, known by its initials as Bacura, near Kingston upon Thames, just outside London. She abandoned the Cambridge Fellowship for it, And to the people around her, and perhaps to the people telling her story afterward, this might have looked like a step down. From the ancient towers of Cambridge to a research association studying coal. From pure science to something that sounded almost industrial, almost humble. Coal, the black rock that heated houses and drove trains and powered the factories, the least glamorous substance imaginable. But this is exactly where the ordinary telling of her life goes wrong, and where ours is going to slow down and pay attention. Because this humble-sounding coal was about to become the making of her. It was in this unglamorous place, with this unglamorous material, that Rosalind Franklin was going to do the first-rate science that made her name. This is where the young woman who had decided at 15 to be a scientist actually became one, fully, publicly, on the record. And she did it years before anyone had ever heard of a photograph called 51. So let us go with her, out of Cambridge, out from under the shadow of a supervisor who did not suit her and a university that would only give her half a degree, and down the road toward Kingston, toward a wartime laboratory and a black rock that most people never think about at all. Let us follow her to the place where she first learned to ask a material what it was made of, and to make it answer. Because there is a way of looking at coal that most of us never manage, and that she was about to master. To you and me, a lump of coal is simply solid and black and dense. But it is not, in fact, simple, and it is not entirely solid. Coal is riddled all the way through with pores, with tiny spaces, an entire hidden architecture of holes too small for the eye to see, like a sponge whose gaps are finer than anything you could ever hold up to the light. And the question of how those pores are arranged, how big they are, how they connect, how much true solid there is once you account for all the empty space, turns out to matter enormously. Not only for understanding coal itself, but for a piece of equipment that was, in that war, keeping people alive. But that is the country we are travelling into next. The country of pores and densities and the clever use of a gas so light it can slip into spaces nothing else can reach. For now, let it be enough to know where she stands. She stands at the beginning of the real work, 21, 22 years old, having already made every choice that mattered. The choice at 15 to be a scientist at all. The choice to go to Cambridge and endure being given only the shadow of the degree she had truly earned. The choice to walk away from an unhappy fellowship and a difficult man rather than bend herself out of shape to stay. And now the choice to spend a war studying coal, of all things, in a plain brick building outside London. Because the work was real and useful and hers. Everything that the world would later argue about, the photograph, the report, the prize, the wrong done to her in a laboratory on the other side of that same city, all of it is still years away, still unimaginable, on the summer night we are drifting through now. She does not know any of it is coming. She only knows that she has decided to understand things, to take the substances of the world in her hands and make them give up their secrets, and that she is very, very good at it. Let that be the picture you carry down with you as you sink a little deeper into the pillow. A determined young woman in the middle of a war, at the start of a life she chose against the gentle current of a family that loved her and did not quite understand her. She has left the ancient towers behind. She is standing in front of the plainest material in the world, and she is about to prove that there is nothing plain about it at all, and nothing plain about her. Outside, wherever you are, the night is doing what nights do. It is holding the world still for a few hours, And here, in this harbour, we have all the time we could want. The whole long, slow length of a life to walk through together, unhurried, gentle, in no rush to reach the parts that hurt. We are only at the beginning. She is only 22. There is coal to understand, and a city called Paris waiting years ahead of her, where she will learn to read a kind of picture almost no one else in the world can read, a skill she does not yet know she will one day need. There are laboratories she has not yet entered, and people she has not yet met. Some who will value her exactly as she deserves, and some who will not. But all of that can wait for the next stretch of the night. For now, let her stand there in the doorway of that wartime laboratory, young and certain and entirely herself, with the whole of her real work still in front of her and none of the sorrow yet arrived. Let the lamp stay low, let your breathing slow to match the slow unspooling of her story. There is nothing you need to do tonight but rest, and listen, and let a life much larger than the legend it became carry you, gently, down towards sleep. So let me tell you where she began, because the beginning matters more than the legend ever admitted. And before I do, if you are new to this harbour, you might drift a little easier, knowing there are more nights like this one waiting for you here, more long, slow lives told in the dark, and you are welcome to stay for all of them. Wherever you are listening from tonight, whatever corner of the world is holding you still right now, you are welcome here. I would love to know where you are, if you feel moved to say, but there is no hurry for that either. Let it wait. Here is the thing that almost no one tells you about Rosalind Franklin. By the time she was 25, she had already made her name. She was a published scientist, respected by people who did not hand out respect easily. And she had never once touched Dina. Not the photograph, not the fibres, not the two forms she would one day tease apart with such patience. None of it. The story the world remembers begins in a darkened room with a single image, and that image did not exist yet, and would not for years. She had done first-rate work before it. She would do first-rate work after it. Tonight we are going to walk through the whole of it, slowly, in order, the way a life is actually lived, and we are going to let the famous photograph take its proper place as one chapter among many, rather than the roof over the whole house. She was born on the 25th of July, 1920, in Notting Hill, in London, the second of 5 children, and she was born into a family that was not merely comfortable but genuinely eminent. One of the old Anglo-Jewish families of London, a family with a long, deep tradition of public service and quiet philanthropy. Her father was Ellis Arthur Franklin, a merchant banker by profession, a partner in the family bank. But he was not only that. In the evenings he taught. He would go to the Working Men's College and lecture on electricity, on magnetism, on the history of the Great War, giving his knowledge away to men who had none of his advantages. That was the temper of the household she grew up inside. Achievement was expected. Service was expected. The only question was in what direction. And the family had reach. Her great-uncle was Herbert Samuel, the first practicing Jew ever to sit in the British cabinet, and later the High Commissioner for Palestine. Her aunt, Helen, whom the family called Mamie, was active in the women's suffrage movement and in the trade unions, a woman who understood before most that other women would have to fight for the plainest kinds of freedom. So Rosalind grew up among people who did large things in the world: law, banking, politics, social reform. These were the honourable paths, the expected paths, the ones a bright child of this family might be steered toward with love. The laboratory was not on the list. And here is the gentle tension that runs underneath her early years, the current she chose to swim against. Her father, who cared for her deeply, was uneasy about a university education for a woman at all. He would have preferred, by some accounts, that she turn her sharp mind toward social work, toward the family tradition of helping others directly. There was real friction over it. Not a cold refusal, not a door slammed and locked, but a genuine unease. A father who did not quite see why his daughter would want to spend her life among instruments and equations when there was so much good to be done in more familiar ways. She did go. Family money and her aunt's support were part of how she got there. But she went knowing that the people who loved her most did not fully understand the thing she was reaching for. She had decided early. She went to St. Paul's Girls' School in London, which was, in those years, one of the very few girls' schools in the whole city that taught physics and chemistry to a serious level, that treated the sciences as something a girl might actually master rather than merely glimpse. And she was good at it. Not just competent. Excellent. She excelled at science and she excelled at sport, and somewhere around the age of 15 she is said to have simply announced it, the way certain people announce the thing they already know about themselves. She was going to be a scientist. Not might be, would be. At 15, in a family and a country that offered a girl 100 quieter futures, she had chosen the one that was hardest to reach. In 1938, she went up to Newnham College, Cambridge, to read the natural sciences, and here the world put its first real obstacle in front of her, though she could not have called it that at the time, because it was simply how things were. Cambridge, in those years, did not grant women full degrees. A woman could sit the same examinations as the men, she could do the same work, attend the same lectures, earn the same marks, and at the end of it she received what was called a titular degree, the title of the thing without the thing itself, not the full Bachelor of Arts. The University of Cambridge would not award women full degrees until 1948, 10 long years after she arrived, so the pattern was already there, waiting for her, built into the stone of the oldest institution she would ever pass through. It was not personal. That is what makes it worth pausing on. It was structural, impersonal, a rule that applied to every woman who walked those courts, and Rosalind Franklin walked into it at 18 and simply kept going. Her graduate year did not go easily. She spent it working under Ronald Norrish, a physical chemist who would one day win a Nobel Prize of his own. And the two of them did not get on. She found him obstinate, difficult to work with, and by every account the year was an unhappy one, a poor match of two strong and stubborn temperaments. It is worth remembering, on a night like this, that even the people who become legends have years like that. Years where the work is a grind and the person you answer to does not see you clearly and the future is not yet a shape you can trust. She had chosen this life against the gentle pull of everyone who loved her, and now she was inside it, and it was not yet giving her much back. But something was about to change. Not in Cambridge. Somewhere quieter and stranger and far more useful than anyone would have guessed. The British Coal Utilisation Research Association was not a romantic place to find your vocation. It sat near Kingston upon Thames, a practical institution doing practical work in the middle of a war that had made the practical suddenly urgent, and in 1942. Rosalind Franklin arrived there and abandoned what remained of her Cambridge fellowship, and began, without quite knowing it, to become the scientist she would be for the rest of her life. Coal, not the glamour the word science sometimes promises, not the white coat in the gleaming laboratory, not the apparatus of a great university, not the sense that you are standing at the frontier of something vast and philosophical. Coal was old and dark and industrial, and people had been burning it for centuries without understanding what precisely it was made of at the scale too small to see. And that was exactly the kind of problem that suited her. Not the problems that came with fanfare and a clear address, but the ones that required patience and methodological precision, and a willingness to sit with imperfect information until it gave up something true. The war needed coal, needed it specifically in the form of activated carbon, which was what the filters in gas masks were made of. A gas mask works because the activated carbon inside it has, at the scale of molecules, an enormous amount of internal surface area, a surface riddled with pores so fine that a single gram of the material contains enough internal surface to cover something close to a tennis court, all of it folded and compressed into a dark granule smaller than a pea. The gas molecules moving through the filter encounter that surface and adhere to it, and the soldier or the factory worker or the civilian breathes air instead of whatever the war has put into the air. That is the mechanism. And the mechanism only works if the carbon has the right kind of pore structure, the right distribution of very small spaces, fine enough to trap the molecules you want to trap, without trapping so many molecules of ordinary air that the mask becomes impossible to breathe through. Rosalind Franklin's job, in part, was to understand that structure, to learn what coal actually is at the level below what any microscope of the era could reach, to characterize the way its interior is arranged, and to do that by measurement rather than by assumption. The method she worked with was elegant in its indirectness. You cannot see a pore too fine to catch light, but you can fill the pore with something and measure how much fits. She used helium gas for this. Helium, the lightest of the noble gases, whose atoms are small enough to penetrate even the finest pore structure of a carbon material. And by measuring how much helium a sample could hold and comparing that with its bulk volume and weight, she could determine what she called the true density of the carbon. Not the density of the carbon as a lump, which includes all the air-filled space inside it, but the density of the carbon itself, the solid matter between the pores. From true density, carefully compared with apparent density and with the theoretical density of perfect graphite, you could read the pore structure the way you read a text, not by holding the pores themselves, but by holding the numbers they leave behind. This is not simple work. It requires hands that know when a measurement is drifting, and minds that know what a drift means, and notebooks that are honest about uncertainty. And Franklin's notebooks were honest about uncertainty. She was 22 when she began this work, and 25 when she finished it, and in those 3 years she published results in the Journal of the Chemical Society and the Transactions of the Faraday Society. Journals that other physical chemists read and cited, journals where you placed your work if you intended it to be taken seriously. And the work was taken seriously, because what she found was not only practically useful for the wartime question of gas mask performance. It was something more fundamental. She found that not all carbons are alike in the way that matters, which is to say the way they change when you heat them. If you take a coal or a carbon material and heat it to very high temperatures, thousands of degrees Celsius, some carbons will rearrange themselves toward graphite. the highly ordered layered structure of pure carbon that is, in a sense, the most organized thing carbon can become. Their layers will straighten and align and approach the regularity of the crystal. And some carbons will not do this, no matter how hot you make them. They will resist the rearrangement, stay disordered, stay glassy and irregular, preserve the chaos of their origin even at temperatures that would melt iron. Franklin named these two categories: graphitizing carbons, which would move toward order with heat, and non-graphitizing carbons, which would not. The classification sounds simple when it is stated plainly like this, and it is, in the way that all true distinctions are simple once someone has made them clearly for the first time. Before she made it, the distinction was blurred, or rather the field had not organized its observations around it in a way that made the difference visible and usable. She made it visible. She measured it in samples across a range of temperatures of carbonization, systematically, and she showed that the microstructure of a carbon material, its porosity, its density, its capacity to graphitize, was determined by the temperature at which it had been carbonized and by the original character of the coal. This classification is still used, not as a historical curiosity, not as a footnote, but as a working framework in carbon science and materials science, in the intellectual lineage that runs toward carbon fibre and the structural carbons that go into aircraft and bicycles and the walls of modern pressure vessels. When researchers in those fields lay out the basic taxonomy of carbons, the graphitizing and the non-graphitizing, they are using a map that Rosalind Franklin drew. She drew it in her mid-20s in a research association near Kingston upon Thames during a war from helium measurements taken in a practical institution doing practical work. By 1945, she had a Cambridge PhD. The thesis concerned the physical chemistry of solid organic colloids with reference to coal. It is not a title that stops the breath. But the work inside it was hers, original, verified by her own measurements and published in respected journals, and it had already been noticed by people whose notice was worth having. She was 25. She was a published, respected physical chemist, and she had never, not once, touched Dina. That is the fact that the standard telling almost never begins with. The standard telling opens on the photograph, and in doing so it implies that everything before the photograph was prelude, that she existed as a scientist in a holding pattern, waiting to become relevant at the moment of someone else's story. But she had already been relevant. She had already made a contribution that would outlast most of what anyone else in her generation was doing. The coal years were not a prelude. They were a chapter complete in themselves, and they had given her the rigour and the patience and the trust in measurement that she would carry into every room she ever worked in afterward. And then she went to Paris, and the rest of her life became possible. The Laboratoire Central des Services Chimiques de l'État was a government laboratory, a French institution with a French culture, and Rosalind Franklin arrived there in 1940, 3 years after the liberation of the city, and found something she had not quite found before: a working environment that suited her. Not perfectly. No working environment ever suits anyone perfectly, and she was a precise and sometimes impatient person who knew when the science was sloppy and did not stay quiet about it. But well enough that for 3 years she was happy in the way that is rare and worth marking, happy in the work and happy in the life around it. The work was crystallography. More specifically, it was X-ray diffraction applied to materials that do not diffract cleanly, not perfect crystals with their tidy regular lattices, but amorphous and semi-ordered substances, carbons, still, and materials like them, where the order is imperfect and partial and the diffraction patterns are broad and blurred rather than sharp and precise. The man who taught her this was Jacques Méron, who led the group in Paris and who was himself a specialist in this particular and technically demanding corner of the field. X-ray diffraction. For anyone who has not encountered it and is finding their way to sleep through the sound of these words, works on a principle that is almost beautiful in its indirectness. You cannot use light to see the arrangement of atoms in a material. Atoms are far too small for light waves to resolve, the way you cannot see individual threads in a piece of cloth from across a room. But if you shine X-rays through the material, the X-rays scatter off the atoms in ways that depend on how the atoms are arranged. The scattered X-rays make a pattern on a detector, a pattern of spots or rings or arcs, and from the geometry of that pattern, if you know how to read it, you can work backward to deduce the arrangement of the atoms that made it. The pattern is not a picture of the structure. It is a kind of shadow of the structure, a mathematical transform of the structure. And the work of the crystallographer is to translate from the shadow back to the solid thing that cast it. This translation is hard under any circumstances. It requires mathematical knowledge and physical intuition and a great deal of practice, and it requires, above all, clean data, diffraction patterns that are sharp and interpretable. For perfect crystals, the patterns can be extraordinarily sharp, and the translation, though laborious, is well defined. But for imperfect materials, for the carbons and amorphous substances that Franklin had been studying, the patterns are smeared and complicated by the disorder itself, and the translation becomes something more like an art, requiring not only mathematical technique but a particular sensitivity to what information is still present in a blurred pattern. What can be extracted and what cannot? What is signal and what is noise? Jacques Méron was expert in exactly this, and he taught Rosalind Franklin, through 3 years of daily collaboration, how to do what he could do, how to read the imperfect patterns, how to extract structural information from materials that did not cooperate with the crystallographer's standard tools, how to work at the edge of what the technique could see and still arrive at something true. She learned it thoroughly. She published in the Paris years more carbon work, extending the framework she had built at Bicura, refined now with the diffraction techniques she was acquiring, and the papers were received well. But more important than any single paper was the skill itself, the capacity she was building, the expert's knowledge of what X-ray diffraction could and could not do with disordered matter. She did not know yet that she would need it. She could not have known that in a few years she would stand before a substance even more disordered, even more reluctant to diffract cleanly than the carbons she was studying, and that everything Méron had taught her would be the difference between a clear answer and a blur. Adina fibre is not a crystal. That is the thing the standard telling sometimes glosses over, because it makes the making of photograph 51 sound inevitable, as though any competent person with an X-ray machine could have produced it. They could not. Adina fibre is a tangle of long molecules arranged with only partial order, and the diffraction pattern it produces is not the sharp constellation of spots you get from a perfect protein crystal. It is something fuzzier and harder and more contested, and the skill required to get anything clean out of it, to control the sample, to set up the experiment, to choose the right conditions, was precisely the skill that Rosalind Franklin had spent 3 years acquiring in a Paris laboratory under a man who specialized in difficult materials. She had been apprenticed, without knowing it, for the specific problem she had not yet been given. But before King's College and the problem and the photograph, there was France itself. She loved it. That is not too strong a word given the sources. The letters she wrote from Paris to family, to friends, are full of it. The food, the markets, the cafes where the argument was part of the pleasure and not something to be smoothed over, the mountains to the south and east that she went to when she could. She was a mountaineer. That word also wants some weight given to it, because it is not the same as someone who enjoys a walk in the hills. She climbed. She went into the Alps, and she climbed, with the physical confidence and the willingness to be cold and tired and uncertain of the footing that real climbing requires, and she loved that, too, with the same direct, physical commitment she brought to the science. There is a version of Rosalind Franklin that exists in many retellings as a purely cerebral figure, all laboratory and ambition and thwarted genius, and it is incomplete. She was also a body moving through mountains, also a person sitting at a table in a Parisian café drinking wine she knew something about, also someone who had learned, as she told it, that the French had a relationship to lunch that the English had entirely failed to develop. The French scientific culture suited her in ways the English one had not. She was direct. She said what she thought about the data and about the interpretation and about the experiment, and she said it clearly and without the softening that English professional culture often seemed to expect, and that she had never quite been able to deliver. In Paris, this directness was not a difficulty. The French scientists argued with each other as a form of respect, as evidence that they were taking the work seriously, and she could argue back, and the argument was the collaboration, and that was how good science got done. She was, by the accounts that survive her, warm with people she liked, and abrupt with people who were sloppy and completely uninterested in performing a modesty she did not feel. She was not modest about what she knew. She was not falsely uncertain about measurements she had made carefully, and in Paris this was not a problem. It would become one, later, in a different room in a different city, with different rules about how a woman in a laboratory was supposed to carry herself. But that was later. And on a quiet night, sitting with the shape of a life, it is worth lingering in the Paris years a little longer than the summary usually allows. 3 years is a long time. In 3 years you learn a place, and it learns you, and the person you are when you leave is not the person who arrived. She had arrived as a physical chemist whose technique was systematic measurement, helium densities and careful notebooks, and the classification of carbons by their behavior at high temperature. She left as something additional, a crystallographer, someone who could look at the blurred and complicated output of an X-ray diffraction experiment on a disordered material and read it, not perfectly, not with certainty, but with the informed judgment of someone who had done this work every day for 3 years under a man who had done it for 20. She left in 1950. She was 30 years old. She had a Cambridge PhD and a body of published work and a new technical skill that placed her among a small number of people in the world who could do what she could do, and she was leaving the city she loved to go back to England and start again. The fellowship that brought her back was at King's College London, a Medical Research Council fellowship in the biophysics unit led by a man named John Randall. The terms of it, as she understood them, were that she would lead the X-ray work on DNA more or less independently, bringing her crystallographic expertise to a biological molecule that the unit was trying to understand structurally. DNA was, by 1950, already known to be the carrier of genetic information that had been established in the mid-1940s by Oswald Avery and his colleagues, though the scientific community had been slow to absorb it, and its structure was one of the outstanding problems in biology and physics and chemistry all at once. The kind of problem that sat at an edge between disciplines and drew people who could move between them. Rosalind Franklin was the kind of person who could move between them. She had spent a decade moving between chemistry and physics, between the practical and the theoretical, between coal and crystallography, and now here was a problem that needed precisely the skills she had. She would work on non-graphitizing using X-ray diffraction, the technique of imperfect materials that Meringue had taught her, and she would approach the problem with the same systematic patience that had produced the carbon classifications. She arrived at King's in January of 1951. And there was a letter. The letter had been written before she arrived by John Randall to sort out the arrangement of the lab. And the arrangement it described, depending on who read it, described something quite different. To Franklin, it described her as the head of the X-ray crystallography work on Dina, the scientist who would define and lead that line of research. To Maurice Wilkins, who had been working on Dina at King's before Franklin arrived, who had taken the first grainy X-ray images of NAFEBs the previous year and had shown them with excitement at a conference, the arrangement meant something else. Wilkins was away when Franklin arrived, and when he returned, he understood, or believed he understood, that she was joining as a colleague, perhaps a collaborator, on work that he had already begun, and that was, in some sense, his. Neither of them was simply inventing their interpretation. The arrangement was genuinely muddled, a failure of administrative clarity at the level of the person who ran the unit, and it curdled before it had a chance to work. This will need to be returned to in more detail, because the consequences of that muddle ran in one direction for years. But for now, in the second month of 1951, Rosalind Franklin was setting up her apparatus at King's College London, and she had Raymond Gosling, a PhD student who had been assigned to her, working beside her, and she was about to begin the most technically demanding and the most consequential X-ray diffraction work of her life. The work on coal had been first-rate. The Paris years had built the skill that made the next work possible. And now, in a biophysics unit in London, with a student and an apparatus and the methodological discipline she had been refining for a decade, she turned toward Dina. She would not know, for a long time, exactly what was being done with what she found. And Dina, it turned out, was exactly the kind of problem she had spent her whole career preparing for. Not a clean crystal, not a material that yielded its secrets readily to the diffractometer. A fibre, long and tangled, with a structure that shifted depending on conditions so subtle that earlier workers had blurred everything together without realizing the blur was the problem. She would spend months sorting out those conditions. She would learn, slowly and carefully, that Dina was not one thing, but two, that there were two forms of the molecule, as different in their diffraction behavior as chalk from cheese, and that the failure to separate them was why the field had been confused. She did not make this discovery quickly. She made it by the method that had always served her: systematic measurement, controlled conditions, honest notebooks, and the refusal to trust a result she had not verified. The apparatus came first. She and Gosling refined the X-ray equipment, adjusted the geometry of the beam, worked on the sample preparation. And then she began to experiment with humidity. Dina changes when it gets wet. That is a simple statement for a fact that took real experimental ingenuity to make useful. Adedna fibri, if you allow it to absorb moisture from the air, transitions from one structural form to another, and the transition changes everything about how it diffracts. The crystalline form, the one she would come to call the A form, appears at lower relative humidity, when the molecule is relatively dry, and it produces a diffraction pattern that is sharp and detailed and crystallographic in the usual sense. The paracrystalline form, the B form, the form that the molecule takes when it is more fully hydrated, closer to the condition it exists in inside a living cell, produces a different pattern entirely, broader in some respects, with a distinctive set of features that encode the helical structure of the molecule if you know how to read them. Franklin knew, because her training with Mering had given her the knowledge, that these two forms had to be studied separately. You could not take a sample that was switching between them as the humidity in the room fluctuated and expect the pattern to tell you anything coherent. The blur that had confused earlier workers was not mysterious once you understood what was happening. It was the blur of two superimposed patterns, two structures averaged together by conditions that nobody had thought to control precisely. She controlled them. She used salt solutions, different salts in different concentrations, chosen because each salt holds the surrounding air at a characteristic humidity to set the water content of the dinafibres precisely and hold it there. The A form at one humidity, the B form at another. Two clean experiments instead of one muddy one. This was the methodological insight that opened the way to everything that followed, and it was the kind of insight that looks simple in retrospect and is not simple at all until someone with the right background and the right training and the right habits of experimental care thinks to ask the question precisely enough to see the answer. She was 31 when she began this work. She had been a scientist, in earnest and in publication, for nearly a decade. The patience she brought to the humidity experiments and the two-form separation was not beginner's patience, the patience of someone who has been told that science requires it. It was the patience of someone who had measured coal pore structures with helium gas and spent 3 years reading blurred diffraction patterns in Paris and knew from long experience that the material gives up something, true only to the person who has taken the trouble to ask the question. The right way. She was taking the trouble. And on a night in May of 1952, with the humidity controlled and the dinafibres in its B form, the more hydrated and more structurally fluid of the two, she and Raymond Gosling made an exposure. The exposure ran for a long time. On the order of 100 hours, accumulated. Not 100 hours of continuous attendance, but 100 hours of X-ray beam passing through the fibre and scattering off its structure and building up the image, slowly, on the detector. The equipment required a fine focus X-ray tube and the right geometry and the stable humidity and all the other preparations that they had spent months refining, and at the end of it, when the image was developed, it showed something that even now, looking at it reproduced in books and articles and on screens, is unmistakably striking. A cross. An X-shaped pattern of dark arcs spreading from the center of the image in 4 directions. Regularly spaced, precise, clear, the signature of a helix. If a long molecule wins in a helix, a spiral like a spring, and you send X-rays through it, the diffraction pattern you get has a characteristic cross shape. Because the helix has a repeat along its axis and a periodicity around it, and these two periodicities combine in the geometry of diffraction to make the X. The bigger the X is, the tighter the helix. The spacing of the arcs encodes the dimensions of the repeat. The image was photograph 51. She knew what it was telling her. She had the training to read it, the Paris years and the meringue apprenticeship, and the months at King's sorting out the A form from the B form, and she extracted from the pattern the quantitative parameters of the helix, the dimensions, the spacing, the pitch of the repeat, the high water content that the B form held, and she knew she was looking at the shape of something fundamental. Not just the shape of a molecule, but the shape of how information is stored in living things, the physical form of inheritance itself. And she continued to work. There was more to do. The A form, drier and more crystalline, was the one that would yield the most detailed crystallographic analysis, and she worked on it with the full rigor of her training. From the A form, she extracted something that mattered in a way that is still not as well known as the photograph, the space group of the Dina crystal. The space group is a mathematical description of the symmetry of a crystal, the set of symmetry operations, rotations, reflections, translations that leave the crystal looking the same. Crystallographers use space group notation as a precise language for describing how the molecules in a crystal are arranged relative to each other, and the space group can, if you know what it means, tell you things about the structure of the molecule itself. The space group she worked out from the A-form data was called face-centered monoclinic C2. The name means almost nothing to most people who hear it, and on a quiet night it is not important to hold on to it, to turn it over and check it, to demand that it be fully understood. What is important, and what will come back later in this story, is that the C2 symmetry told a structural story. It said that the Dina molecule in the A-form crystal had a particular kind of internal symmetry. And that symmetry had implications for how the two strands of the molecule, because there are two, as Franklin's data made clear, must be oriented relative to each other. The two strands must run in opposite directions, not both pointing the same way, like two parallel roads, but anti-parallel, like two one-way streets running toward each other. She put this in a report. The report was a Medical Research Council progress report, a summary of the work her group had done, written in December of 1952. It contained the measurements from photograph 51. It contained the C2 symmetry finding and what it implied. It contained the quantitative parameters of the helix. It was not a published paper, it was an internal document. A report to the body that funded the unit, a progress summary of the kind that any research group produces as a matter of administrative record. She filed it and continued working. She did not know, in December of 1952, what would happen to the report. She did not know who would read it, or in what context, or what they would do with what they found inside it. She was focused on the science. She was focused on the A form and the B form, and the measurements that might, with more work, resolve into a complete and defensible structural model. She was rigorous, and she was patient, and she was still working on the problem the way she had always worked on problems, not by leaping to an answer that felt right, but by nailing down the evidence until the answer became the only possibility remaining. And somewhere in Cambridge, two men were also thinking about Dina. And somewhere in Cambridge, two men were also thinking about Dina. But that part of the story belongs to what comes next. Before we follow it, we need to understand what she had built, and where she had built it, and how long it had taken. Because the photograph that would pass out of her hands was not something that happened to her. It was something she made. She arrived at King's College London in January of 1951. The position was a Medical Research Council research fellowship attached to the biophysics unit that John Randall ran. Randall was a physicist of some standing, a man who had contributed to the development of the cavity magnetron during the war, a device that had improved radar sufficiently to matter, and who had subsequently turned the biophysics unit at King's into a place of genuine scientific ambition. He wanted X-ray work done on biological molecules, and he wanted someone who could do it properly. Franklin's reputation from Paris had reached him. Her papers on carbon and on the diffraction of disordered matter had circulated in the circles that paid attention to such things, and Randall understood what it meant to be able to extract structural information from something that would not cooperate by forming a neat, regular crystal. Nafibras were not neat, regular crystals. Nafibras were difficult. He wrote to her. The letter he sent to Rosalind Franklin, and the understanding it created in her mind about what she would be doing at King's, and the understanding that already existed in Maurice Wilkins's mind about what she would be doing at King's, these were not the same. Randall's letter told Franklin that she would have the X-ray crystallographic study of Na as her primary responsibility, that Gosling, a PhD student who had already been working on the problem, would be assigned to her, and that the work was hers to lead. This was not unreasonable language. It was the language of a department head allocating a specific project to a specific person with specific skills. But Maurice Wilkins had been working on Dina at King's already. He had taken some early X-ray photographs himself. He had been away when the arrangements were made. The timing, as with so many of the things that would later need explaining, was imperfect, and when he returned, he found a physical chemist with a Paris pedigree and a manner he described as formidable, installed in a laboratory that he had understood, in his own way, to be part of his territory. Neither of them was simply wrong. The arrangement was genuinely muddled from the top. A failure of administrative clarity that had been allowed to calcify into a professional antagonism before either of them had done anything to cause it. The misunderstanding that poisoned the collaboration at King's was not born of malice on any side. It was born of a letter that said one thing to one reader and implied something different to another, and of two serious, proud scientists, neither of whom found it easy to back down. The atmosphere at King's did not help. The senior common room, where the senior academic staff dined, was not open to women. This was not a policy at every institution in London, and it was not universal even in that era, but it was the policy at King's in the early 1950s. The table, where colleagues talked and relaxed and argued about science over lunch. The informal space, where so much of the connective tissue of a department is woven, was not available to Franklin. She ate elsewhere. The cold she described in her letters was partly the temperature of the institution itself, partly the specific chill of a collaboration that had been broken before it began, and partly the ordinary difficulty of being a woman in a department that had not yet worked out what to do with one. She was rigorous and direct and impatient with imprecision, and in Paris those qualities had been welcomed, had made her a valued member of a group that argued hard and respected each other for it. In the Kings of 1951, they were read differently. A direct woman was a difficult woman. An impatient woman was a cold one. She was neither cold nor difficult. She was someone who had found, in France, that her way of working suited the people she worked with, and who had not yet found that in London. But she had the laboratory, she had the X-ray equipment, she had the problem. And she had Raymond Gosling, Gosling was a PhD student, 24 years old when Franklin arrived, and he became her collaborator in the most immediate and practical sense, the person who was in the room, who learned to adjust the apparatus, who understood the daily rhythms of a diffraction experiment and the small catastrophes that could ruin one. He was, by his own later accounts, deeply impressed by her. She was systematic in a way that he had not previously encountered. She knew what she was doing with an X-ray camera, and she knew it with a precision that came from years of practice on carbon, on coal, on every variety of disordered and uncooperative material that Mirong's Paris laboratory had presented to her. She looked at a diffraction image the way a doctor reads a scan, not just seeing, but interpreting, knowing what each shadow and smear and bright spot meant about the thing that had cast it. The apparatus at King's needed work. The X-ray sources of the period were not uniformly reliable or uniformly sharp, and a diffraction experiment on something as finicky as a dinar fibre demanded a fine focus tube, a source that could produce a narrow, bright beam rather than a broad, scattered one, because a broad beam means a blurry image, and a blurry image means measurements you cannot trust. Franklin and Gosling refined what they had. They adjusted. They were patient with the machinery the way a craftsman is patient with a tool that has not yet been properly tuned, and in time the camera behaved better, and the images it produced grew cleaner. But the larger problem was the dinar itself. A dinar fibre stretched between 2 points and placed in the X-ray beam is not a simple object. Its structure, the arrangement of atoms along its length, depends critically on how much water it holds. The molecule is surrounded by water in the living cell. Remove that water and the structure changes, tightens, rearranges itself into a different configuration. Add it back, and it changes again. These were not minor variations. These were two distinct and different forms of the same molecule, and they produced two distinct and different X-ray diffraction patterns, and if you did not know that, if you were not carefully controlling the water content of your sample, you would be photographing a mixture of the two forms and trying to interpret a superimposed blur of signals that belonged to different things. This was not immediately obvious to everyone working on dinar at the time. The techniques for controlling the hydration of a biological sample precisely enough to keep it in one form or the other were not standard. But Franklin understood the principle. She had spent years thinking about how the internal structure of a material responds to its environment, how the pore structure of a carbon changes with temperature, how a substance's behavior under a measurement tool depends on what state you have coaxed it into, and she designed the solution. Salt solutions. Carefully prepared mixtures of water and salt, their concentrations adjusted to produce specific levels of humidity inside the camera. The fibre sits in the beam, and around it the air is held at a controlled humidity by the vapour above the solution, and the molecule draws in water or releases it until it reaches an equilibrium with its surroundings. By changing the salt concentration, you change the humidity, and by changing the humidity, you change the state of the dinar. You move it between forms. You can keep it in one form and photograph it cleanly, and then you can shift the conditions and photograph the other form cleanly, and you have two separate, legible images to work with, rather than one muddled, uninterpretable one. This methodological care, knowing that the forms needed to be separated, and building the experimental conditions to separate them, was itself a significant contribution. It is not a flashy contribution, the kind that announces itself in a headline. It is the kind of contribution that is invisible unless you know what you are looking at. the kind that makes everything downstream possible and receives very little of the credit for it. She named the two forms. The drier form, the one that formed when much of the water had been drawn out, she called the A form. It was crystalline, its atoms arranged in a regular, repeating pattern, and it produced a complex, intricate diffraction pattern full of detail, the kind of pattern that, if you were patient and skilled enough, you could analyze to extract precise atomic coordinates. It was beautiful, in the sense that the tools of X-ray crystallography had been largely developed on crystalline materials and were well suited to reading one. But the molecule in this state was not in the state it occupied in the living cell. It was a compressed and dehydrated version of itself. The wetter form, the one that the fibrae adopted when the humidity was high, she called the B form. This was the paracrystalline form, not quite fully ordered, the molecules retaining some of the flexibility and irregularity they had in solution. Its diffraction pattern was simpler than the A forms, less information-rich in one sense, but it had a quality that the crystallographer immediately noticed. It was cleaner. It was more legible in the specific sense that its major features stood out without ambiguity. If the A form was a dense text that would require years of patient analysis to decode, the B form was a diagram with clear lines. Franklin recognized this. She recognized it precisely. She understood that the two forms were different states of the same molecule, that they required different experimental conditions and different analytical approaches, and that confusing them, or working with a mixture of both, was a path to unreliable results. She decided to proceed with the A form for her primary crystallographic analysis. Because the A form held more information, and because she was a crystallographer of rigorous instinct who wanted to extract the full structural picture before committing to a model. The B form, she noted. She photographed it. She set the data aside. In May of 1952, she and Gosling produced the image. The B form of Dina, at high humidity, in the fine focus X-ray beam that they had spent months preparing and refining. The fibre stretched across the camera, the salt solution holding the air around it at the right humidity to keep the molecule fully extended and hydrated. The shutter open, the beam on. The exposure ran for the better part of 100 hours. This is not a typographical error. 100 hours, more or less, the exact figure is in the range of tens of hours of accumulated exposure, because X-ray diffraction of a biological fibre is not a quick process. The X-rays are scattered off the atoms in the molecule, and the scattered X-rays make a pattern on a piece of photographic film, and the intensity of the pattern at any given point depends on how many X-rays have landed there. A faint signal requires a long exposure to build up enough intensity to be visible. The molecule is small. The scattering is weak. You wait. They waited. And what the film recorded when it was developed was photograph 51. It is a simple image by the standards of a modern display. Dark, mostly, the unexposed film that the beam did not reach, with a bright central spot where the direct beam passed through. But arranged around that central spot, in the shape of an X, 4 arcs of brightness, 2 above the centre and 2 below. Leaning in toward each other like the arms of a cross, was the signature of a helix. The geometry of a helical molecule produces exactly this pattern when X-rays pass through it and are scattered, 2 pairs of arcs, making an X shape. The angle between the arms related to the pitch of the helix, the spacing between the arcs related to the diameter. The distribution of intensity along the arcs, carrying information about the arrangement of the atoms within. Franklin read the image. She measured it. She was trained for this, had been training for it, without knowing it, since her first months in Morang's laboratory in Paris, learning to read diffraction images from things that did not behave like textbook crystals. Adina Fibre was not a perfect crystal, and what Mering had given her was the skill to think carefully about imperfect and disordered matter, to know which features of the diffraction pattern were signal and which were artifact, to work confidently with the real rather than the ideal. She had come to King's with that skill already developed. She had spent the previous months honing the experimental conditions until they produced the cleanest possible image of the most hydrated possible form. The photograph was not a lucky accident. It was the product of a specific expertise, built over years, deployed deliberately. From the image she extracted numbers. The pitch of the helix. The distance along the molecule's axis for one complete turn was 34 angstroms. The diameter was approximately 20 angstroms. The molecule contained a very high proportion of water, far more than many of the proteins that had been studied by X-ray methods, which meant that the molecule in the B form was extended and open, its chains well separated. These were real measurements, precise enough to build a model from, and they were written down. She continued with the A form. The A form was the harder problem, and the more interesting one to her at this stage, because it was the one that could in principle yield a complete atomic level structure through the established methods of X-ray crystallography. Photograph 51 was data on the B form, vivid, clear, the helix signal unmistakable, but the B form, because it was disordered, could not be fully solved by the same crystallographic methods that applied to the A form. The A form, with its regular crystal packing, was where the detailed work lay. From her analysis of the A form, she extracted a symmetry. The unit cell of the crystalline A form, the smallest repeating unit of the crystal, the block that tiles itself to fill the whole structure, belonged to a space group known as C2. This was the face-centered monoclinic C2 space group, a designation that carries within it a specific set of symmetry operations. A precise description of how the atoms in the unit cell are related to each other by rotation and reflection. And one of those symmetry operations had an implication. The C2 space group applied to a molecule like DNA, a molecule with two strands, which her data clearly indicated, required that the two strands be related to each other by a specific kind of symmetry. The symmetry between the two strands is a dyad, a twofold rotational axis, a way of turning the molecule 180 degrees and finding that it looks the same. The only way a double-stranded helical molecule can be related by a dyad is if the two strands run in opposite directions. The same principle that allows you to rotate a molecule and find it unchanged forces the two strands into an antiparallel arrangement. They cannot both point the same way. The chemistry, the geometry, and the symmetry of the crystal all converge on the same conclusion. This was not a guess. It was not a hunch or an inspired intuition. It was the kind of inference that a trained crystallographer makes from a symmetry classification, the kind that follows from the mathematics of how crystals are built, and that is defensible in the most rigorous sense. Franklin had measured the unit cell. She had determined the space group. The antiparallel conclusion followed from the measurement the way a logical consequence follows from its premises. She put all of this into the December report. The Medical Research Council Progress Report, written in December of 1952, was the document in which she gathered the results of nearly 2 years of work. It contained the B-form measurements from photograph 51, the pitch, the diameter, the water content. It contained the A-form analysis and the C2 space group determination. It contained the implication for the strand orientation, the anti-parallel arrangement that the symmetry demanded. It was a report, not a publication, not formatted for a journal, not refereed, not presented as a finished argument to the outside world, but as a record of what the work had established. It was thorough and precise. She filed it. She continued working. She was still focused on the A-form, still pursuing the complete crystallographic analysis that she believed was the right way to proceed, still unwilling to leap to a structural model before the measurements justified one. The approach was principled. The approach was also, in the light of what followed, something that historians have discussed with care, because the question of whether Franklin was close to solving the structure of Dina before Watson and Crick announced their model is genuinely open, and the honest answer is that we do not fully know. Her notebooks show her moving methodically through the problem. She held the key measurements. She had identified the correct space group, and the space group carried the anti-parallel answer inside it. But she had not yet published, and she had not yet built a model, and the question of how long it would have taken her to convert the measurements into a complete defended structural model is something the record cannot answer with certainty. She was not slow. She was careful. There is a difference. The scientific culture of the early 1950s was one in which model building was a somewhat contested practice. Linus Pauling had used molecular models to propose the alpha helix structure for proteins, and the approach had been broadly successful, but it was also one that could, if conducted too speculatively, produce models that were elegant and wrong. Franklin's instinct was to stay close to the data, to ensure that what she built was defensible rather than premature. This was not timidity. It was a commitment to doing the thing right rather than doing it first, and it was continuous with everything she had done in her career from the coal measurements at Bicura onward. The report sat in December of 1952. The photograph sat in the laboratory. She did not know, and could not have known, what was already in motion around her. The conversations in Cambridge, the people thinking about the problem from a different direction, the circumstances that would bring her data into a room she would not be present for. She was a scientist, doing science, in the way she had always done it. She had no reason to believe that the progress report of a medical research council unit would leave the committee that funded it. She had no reason to believe that the B-form image, filed under its number in the laboratory record, would leave the building. She was working. Outside, London in the early 1950s carried on in the way it does. The particular grey and busy way of a city, still in the slow process of recovering from a war, still finding its new shape, still learning to be what it would become. King's College sat on the Strand, along the Thames, a short distance from the concentration of barristers and courts that lined the street, not far from the river that had run through the city for a longer time than almost anything else that had run through it. In the building's biophysics unit, in the laboratory with the X-ray camera and the humidity-controlled sample holder and the photographic film that turned a helix into a cross of light, a woman had spent 2 years measuring the structure of a molecule that most of the world would spend the rest of the century learning about. She did not know, in those December days, that the 2 men in Cambridge were about to be given what they needed. But the report was written. The measurements were real. The symmetry was correct. The photograph existed, sharp and unambiguous, the helix exactly where the physics said it should be, the numbers extracted from it precise enough to matter. Whatever came next, whatever would be done with what she had made, the work itself was her work. The careful months of refining the camera, the decision to separate the A and B forms when others had blurred them, the patient waiting through nearly 100 hours of exposure, the reading of the image and the extraction of the measurements, the sitting down in December and writing the report that described what she had found, all of this was hers, and all of it was done, and none of it could be undone. She filed the report. She continued working. And somewhere in Cambridge, two men were looking at what they had and considering what they still needed, and the new year was approaching. 1953. And the problem that had occupied crystallographers and biologists and chemists and model builders on both sides of the Atlantic was not yet solved, but it was closer to a solution than almost anyone outside a very small number of rooms understood. There was a letter that would start the sequence of events. There was a visit that had not yet happened. There was a moment, not far away now, when a photograph would be looked at by someone who had not made it, who had not waited through the long exposures, who had not worked out the humidity conditions, who had not separated the A form from the B form with the care that produced a legible image rather than a blur, and that person would understand in an instant what he was looking at. But that moment had not yet come. It would come in January of 1953, and when it did, it would come quietly, in the ordinary way that consequential moments so often do. Not announced, not marked, not recognized at the time as the kind of thing that historians would later spend decades discussing. A door opened. A photograph was brought out. A man looked at it. All of that was still ahead. For now, in December of 1952, the report was written and the photograph was filed, and the woman who had made both of them was sitting with the problem. Still working, still precise, still persuaded that the right approach was to follow the evidence wherever it led, and to resist the temptation of a model that arrived before the measurements could support it. She had been doing this since she was 22 years old. She had done it in the mines and in the laboratories and in the basement of a Paris building where Jacques Méran had first shown her what an X-ray could reveal about the secret geometry of matter. She had been building toward this, toward the skill and the knowledge and the specific experimental clarity that the B-form image required, for her entire scientific life. She did not yet know what the report would do. She filed it, and the year turned, and London went quiet for a night, and then resumed, and somewhere across the city the same cold winter sat on Cambridge the same way, and the men thinking about Dina there were also in the middle of a problem that had not yet resolved itself into the thing it was about to become. She had arrived at King's College London in January of 1951, carrying a Medical Research Council fellowship and a reputation that was already, quietly, her own. The biophysics unit there was led by John Randall, a physicist of considerable standing, a man who had played a role in the development of the cavity magnetron during the war and who now presided over a group working at the borders of physics and biology, the borders where the instruments of one discipline were being turned with increasing seriousness upon the materials of the other. It was the kind of research environment that the post-war years in Britain were producing in certain well-funded corners, a crossing place, a threshold where it was not yet entirely clear what the questions were, only that the methods for answering them were becoming available. Franklin understood this. She had been working at exactly such a threshold for years, and yet the arrangement she had understood herself to be walking into was not quite the arrangement that existed when she arrived. There was a letter John Randall's letter, written to her before she came, and the letter described a situation that had a particular clarity to it when read in one direction and a quite different shape when read from another position entirely. Randall had written to Franklin in a way that suggested she would be leading the X-ray work on Dinar, that the project was hers to develop, that she would have the independence she had known in Paris. What the letter did not make adequately clear was that Maurice Wilkins, who had already begun X-ray work on non-fibres at King's, and who had in fact brought the material and the initial ideas to the unit, understood himself to be the one directing that work, and understood Franklin to be arriving in some relation to it that was collaborative, subordinate, something other than independent. Wilkins was away when she arrived. The letter had gone out while Wilkins was absent. And when he returned, and the two of them found themselves in the same rooms working on the same problem, neither of them was simply wrong about what they had been told. The muddle was Randall's, and it was genuine, and it was also the kind of administrative confusion that, in certain climates, between certain temperaments, might have been smoothed over quickly and set aside. Between Franklin and Wilkins it was not smoothed over. It hardened. They worked in the same building for 2 years and communicated, in the end, largely through notes, and the collaboration that might have existed between their 2 lines of work, her crystallographic precision. His accumulated fibres and his own partial data remained unrealized. The environment in which this happened was not warm. The senior common room at King's in those years was, as a matter of institutional arrangement, restricted to male members of the academic staff. The dining and the conversation and the informal exchange that happens in such rooms, the kind that is not scheduled and does not appear on any agenda but that shapes collegial life in ways that are difficult to overstate, that was not available to her. She had colleagues, she was not isolated in any simple sense. But she was navigating a social geography that did not include her in its ordinary traffic, and she was doing it while also managing a scientific disagreement that had been set in motion before she ever walked through the door. What she had was the work, and the work, as it always had been, was very good. Raymond Gosling had been assigned to her as a PhD student. He was young and capable, and together they set about the problem with the methodical seriousness that Franklin brought to everything she touched. The apparatus needed refinement. The conditions under which the fibres were held needed to be controlled with a precision that had not previously been applied. Because what they were working with was not a stable crystal, not the kind of clean, regular repeating structure that produces a textbook diffraction image. Dinar in fibre form was sensitive to humidity, and as the humidity changed, the fibre changed with it, contracting or expanding, shifting between 2 distinct conformations that diffracted in entirely different ways and had to be treated as entirely different problems. This was not a small insight. It was, in fact, the kind of insight that determines whether you produce useful data or whether you spend years looking at a blur and calling it a result. Franklin and Gosling used salt solutions to control the humidity of the chamber precisely, moving the sample between its 2 forms deliberately, learning what each form required, learning what each form revealed. The crystalline form, drier, more ordered, diffracting in a way that rewarded careful mathematical analysis, she called the A form. The other form, more hydrated, paracrystalline rather than crystalline, not as mathematically tractable in the same way, but yielding something unmistakable to the eye if the image was clear enough, she called the B form. They were different structures. They needed different methods. Almost everyone else working on Dinar had been treating the varying images they produced as a single muddled problem. Franklin separated them and insisted on the separation. In May of 1952, with the apparatus refined and the conditions controlled, and the B-form fibrae held at precisely the right humidity for what turned out to be something on the order of 100 hours of accumulated exposure, one of the longest X-ray diffraction exposures that had been used on a biological material to that point. An image appeared on the photographic plate that was different in its clarity from almost anything that had come before it. The reflections arranged themselves in a clear and unmistakable cross, arms spreading outward and upward from a center, the signature, as any crystallographer who had studied helical structures would recognize immediately, of a molecule wound in a helix. She filed the image. She recorded the measurements. She continued working. And the photograph stayed in the drawer at King's College London, labelled and catalogued along with all the others, one data point among many in a programme that was still unfinished, still accumulating, still moving toward the rigorous account she intended to give before she claimed anything at all. January of 1953 arrived cold, the way London Januaries arrive, with a low grey sky that settles over the river and the stone buildings and does not lift for weeks. Maurice Wilkins was in possession of the image. He had not taken it. It had been made by Franklin and Gosling in Franklin's laboratory using equipment she had refined and a methodology she had developed. But it was at King's College, and Wilkins had access to it, and when James Watson came down from Cambridge to visit, Wilkins showed it to him. Watson later described the moment in the book he published in 1968. His mouth fell open, he wrote. His pulse began to race. He saw, immediately and without calculation, the cross of reflections that a crystallographer trained in helical diffraction would read as a helix. He was not primarily a crystallographer. He had not spent years learning to make such images or to interpret them. But the image was clear enough and striking enough that even a non-specialist could see the shape inside it. He saw it. And he remembered it, and he left King's College and went back to Cambridge carrying what he had seen. Franklin did not know that this had happened. There is no record that anyone told her. There is no letter, no notebook entry, no account from anyone who was there to suggest that she was informed that her photograph had been shown to a visitor from another institution. The image she had made, in her laboratory, in her own time, with her own student and her own refinements to a shared instrument, it moved without her. But the photograph was not the only thing that moved. Some weeks earlier, in December of 1952, Franklin had submitted a progress report to the Medical Research Council, which funded the biophysics unit at King's. The report was a technical document describing what the unit had accomplished and what remained to be done. It was the kind of internal accounting document that every research group under public funding was required to produce. In it, she had set down the measurements she had extracted from the A form of DINA, precise crystallographic data, including the symmetry of the unit cell, the way the structure repeated in space. The symmetry she had determined was a C2 face-centered monoclinic space group. That designation has a specific meaning. In crystallography, the symmetry of a space group tells you something about the arrangement of the molecule inside it, about what relationships must exist between one part of the structure and another. For a C2 space group, the structure has a particular twofold symmetry. For a molecule made of two chains, that twofold symmetry means, in the vocabulary Francis Crick knew how to read, that the two chains run in opposite directions, antiparallel, one chain ascending, the other descending, like two staircases wound around the same axis in opposite orientations. This was the clue. Not the photograph, not the cross of reflections. The single letter and number designation in a progress report, C2. Max Perutz sat on the Medical Research Council committee that reviewed the King's biophysics unit. He had access to the report. He shared it with Watson and Crick at the Cavendish Laboratory in Cambridge. Perutz maintained, for the rest of his life, that the report was not formally marked confidential, that there was no clear rule that forbade him from passing it to colleagues, and that he had not understood he was doing anything improper. The matter was debated by historians and scientists for decades after the events, without reaching a settled verdict. What can be said with precision is this: the report existed, it contained Franklin's measurements and her symmetry determination, it reached Watson and Crick. And Crick understood immediately what the C2 designation implied about the orientation of the two chains. Franklin had not shared this material with the Cavendish. She had not been asked. She had not been consulted. She was not part of the conversation in which her own finding was used. The double helix model that Watson and Crick completed in the early months of 1953 was correct. Two chains, anti-parallel, wound around each other in a right-handed helix, the base pairs stacked in the interior like the rungs of a ladder, the sugar-phosphate backbone on the outside. When they published their model in Nature on the 25th of April, 1953, two other papers appeared in the same issue. One was by Franklin and Gosling, presenting X-ray data in support of the helical structure. The other was by Wilkins and two colleagues, presenting further X-ray evidence. The arrangement of the papers, the Cambridge model first, the King's data following, had the effect, whether or not this was intended, of making the crystallographic data look like confirmation of a Cambridge idea. As though Watson and Crick had reasoned their way to the structure, and the X-ray workers had then gone and checked it. That is not quite what happened. The data had been load-bearing. The photograph had shown Watson the helix. The symmetry in the report had given Crick the anti-parallel arrangement. These were not confirmations, they were foundations. But foundations do not appear in photographs of the completed building, and the structure of a scientific paper makes it very difficult to recover the actual sequence of events after the fact. Franklin appears to have known that Watson and Crick had built the model and that it was correct. She went to Cambridge and examined it, and by most accounts she accepted that it was right. She does not seem to have known at that point about the route her data had taken. There is no letter in which she expresses betrayal. There is no record of bitterness about the events of that winter. The image of a woman who died knowing she had been wronged, which has become part of the way this story is told, does not have a strong evidentiary foundation. She may not have known. What she certainly knew was that the problem of dinar had been solved, that her time at King's was nearly done, and that there was other work to go to. She had been asked, or required, the correspondence is part of the historical record, and it is not entirely flattering to those who imposed the condition to leave Dina behind when she left King's College. It was understood that Dina belonged to Wilkins. Whatever she thought of that arrangement, she accepted it. She left in 1953. She did not look back, or if she did not leave a written record of doing so. She went to Birkbeck College, London, to the crystallography laboratory of J.D. Bernal, and she began again. Bernal's group was different from King's in almost every dimension that had mattered at King's. The culture was more collegial, the intellectual atmosphere suited her directness. And the problem she was handed, or chose, was not dinner, but something altogether different, the tobacco mosaic virus. Tobacco mosaic virus had been studied for decades by the time Franklin arrived at Birkbeck. It was the first virus ever isolated in pure form in the 1930s, and it had a feature that made it attractive to crystallographers. It was a rod-shaped particle, relatively long and uniform, and it could be prepared in large quantities for experimental work. The question in the early 1950s was what that rod actually looked like on the inside. How were the protein components arranged? Where was the genetic material, the RNA, housed? Was the particle solid all the way through, or was there something else going on? The prevailing assumption, the answer that most people working in the field had accepted or at least found reasonable, was that the virus was essentially a solid rod. Protein filling the core, RNA embedded somewhere within that mass, a structure that was dense and continuous from its outer surface to its center. Franklin looked at the data and did not find that answer. She and her colleagues, a group that included Aaron Klug and Kenneth Holmes and John Finch, brought the full methodology of X-ray fiber diffraction to the tobacco mosaic virus in a way that had not been done with this degree of rigor before. The work built slowly, as good crystallographic work always does, each measurement checked against the previous one. Each model tested against the full body of data rather than against a selected subset. And what the data showed, when it was assembled carefully and read honestly, was that the tobacco mosaic virus was not solid. The center of the particle was hollow, a hollow tube, not a solid rod. The protein subunits were arranged in a helix. Franklin was working with helical structures again, in a different context, with a different molecule spiraling outward from a central axis that was empty, an axis along which, at a radius of approximately 40 angstroms from the center, the RNA was embedded, not free-floating in a solid core, not dispersed throughout the mass, positioned at a specific radius within the protein helix, held in place by the structure of the protein around it. 40 angstroms. The angstrom is a unit of measurement so small that a single human hair, if you were to slice it into 10 million equal pieces across its width, would give you ribbons roughly 10 angstroms wide. The RNA in the tobacco mosaic virus sat at a distance from the central axis that could be measured, confirmed, described with precision. Franklin measured it. She and her group confirmed it. The virus was hollow, the genetic material was positioned in a specific geometry within the protein, and the whole structure could be described in terms that another scientist, working somewhere else in the world, could reproduce and test. This was not an incremental refinement of a prior result. It was a correction of a wrong assumption, achieved through careful, methodical, technically demanding work. It meant that the way people pictured tobacco mosaic virus, the mental model they had carried, was wrong, and that the correct picture had been worked out by a group in London that was doing the thing science is supposed to do, looking at the evidence and following it where it went, even when it led away from what everyone had expected to find. The work continued. The group extended its methods, refined the models, published results in Nature and elsewhere that accumulated into a body of knowledge about viral structure that was recognized as foundational. Aaron Klug, who had joined her group and who worked alongside Holmes and Finch through these years, would later describe the methods and the intellectual framework he had built during this period as the foundation for his own subsequent research. In 1982, nearly a quarter of a century after Franklin's death, Klug was awarded the Nobel Prize in Chemistry for his development of crystallographic electron microscopy and its application to the structural investigation of nucleic acid and protein complexes, work that traced its lineage directly to the Birkbeck group. to the methods Franklin had developed, to the collaborative atmosphere she had created there. He said so himself. His Nobel lecture names his debts. In 1958, as the virus work was still expanding into new problems, she had begun to apply the group's methods to poliovirus, another rod-shaped particle with its own unresolved questions. Franklin oversaw the construction of a large physical model of the tobacco mosaic virus. It was made to be displayed. It was made for the Brussels World's Fair, for the Expo 58, which drew visitors from across the world to a city still rebuilding its sense of itself in the decade after the war. Among the buildings and the national pavilions and the atomium, the great steel structure built for the occasion, its 9 spheres representing the unit cell of an iron crystal, 9 times magnified to the scale of buildings. Among all of that, there was a model of a virus, her virus, built under her direction, shown to the world. Science does not often make it to world's fairs. The objects that do make it tend to be the ones whose makers are still alive to negotiate and arrange and advocate for them. Franklin had done that. She had taken the work from the bench and the dark room and the carefully catalogued photographic plates and brought it in its large and visible and architectural form to a pavilion in Belgium, where strangers walked past it and looked at it and perhaps did not know whose mind had worked out its shape. She would be dead within weeks of the fair's opening. The ovarian cancer was diagnosed in 1956. She had continued working through the diagnosis, through the treatments, through the periods of remission that a disease like this can offer and then withdraw without warning. The disease moved in the way such diseases move, which is to say with its own timetable and its own indifference to the work that needed doing and the problems that were not yet solved. She died on the 16th of April, 1958, in London. She was 37 years old. The question of what caused the cancer is one of those questions that the record does not resolve, and that it would be dishonest to resolve by choosing a cause for the sake of a cleaner narrative. The years of X-ray work, the long exposures, the close proximity to the equipment, the accumulated dose of a career in experimental diffraction are plausible contributors. The risk is real. But Ashkenazi Jewish ancestry carries an elevated hereditary risk of ovarian cancer, a genetic factor that has nothing to do with laboratories or photographs and everything to do with population genetics and inherited variants in particular genes. Both factors are real, both are plausible, neither has been established as the cause. To say she was killed by her own instrument, the X-ray apparatus she spent her career mastering, is dramatic and poetically tidy, and it may be true. To say it is definitively true would be to choose the story over the evidence. She died at 37 of ovarian cancer, and the rest remains open. 4 years later, in 1962, the Nobel Prize in Physiology or Medicine was awarded jointly to Francis Crick, James Watson, and Maurice Wilkins for their discoveries concerning the molecular structure of nucleic acids and its significance for information transfer in living material. Franklin's name was not on the prize. Franklin was not alive. The Nobel is not awarded posthumously. That rule was formalized in the Foundation's statutes in 1974, but the practice predates the formalization. The committee did not consider candidates who had died, and the prize does not travel to an estate or to a legacy. Beyond that procedural fact, there is a numerical constraint that has received less attention than it deserves. No more than 3 living individuals may share a single Nobel Prize. In 1962, the 3 who received the prize were Crick, Watson, and Wilkins. Franklin was not alive to be counted. But even in a counterfactual in which she had been alive, and in which her contribution had been fully understood by the committee, the three-person ceiling would have required a choice. The choice would have been about priorities and credit and the distribution of recognition in a field where the record was complicated and the contributors were many. None of that makes the exclusion clean. It is not clean. She was dead because she was dead at 37, which is too young, and the work she had done before she died, the coal research, the crystallographic methodology she brought to King's, the photograph, the measurements in the report, the virus work, the hollow core, the Röner positioning, none of it was in the room in Stockholm when the prize was given. The prize went to 3 men, 2 of whom had used her data and 1 of whom had worked in the same building and never found a way to collaborate with her that was not defined by conflict. She was absent. And the Nobel, in the way it works, in the way its statutes are written, did not have a mechanism to account for that absence. To call this a robbery is to import a precision the record does not support. To call it without consequence or complexity is to do the same thing in the other direction. It sits, historically, as a convergence of institutional rules, the timing of a death, the structure of a prize that was never designed to account for the complexity of large scientific collaborations, and the era's treatment of her contribution as secondary, as confirmation rather than foundation. All of those things are true at once. In 1968, James Watson published The Double Helix, a personal account of the events of 1952 and 1953. He called Franklin Rosie throughout, a nickname she had apparently not used herself and had not been called to her face by Watson, as far as the record shows. He portrayed her as a difficult woman, unable to see what was in her own data, resistant to the idea of a helix, a problem to be worked around rather than a colleague to be engaged with. The portrait was unflattering. It was also influential, and it did a great deal of work in fixing a particular image of Franklin in public consciousness, an image of a woman too rigid and too proud to see what she was looking at. Watson included an epilogue. In it he conceded that his first impression of her had been wrong. He conceded that she was a scientist of genuine standing. The epilogue is usually quoted less often than the rest of the book. What the book did, through the portrait and the unflattering nickname and the narrative of the brilliant Cambridge men who had to find a way around the obstinate woman at King's, was make Franklin a figure in someone else's story. And it made the story about her obstruction rather than her contribution, about her failure to see rather than about the long and careful years of work that produced the photograph in the first place. In 2002, Brenda Maddox published a biography. The title was Rosalind Franklin, the Dark Lady of Dina. The Dark Lady, a phrase that had been used of her at King's, an epithet that combined otherness with difficulty in the way such epithets tend to do. Maddox's book was the corrective account, the one that went back to the primary sources, the letters and the notebooks and the published papers and the accounts of the people who had actually known her, and tried to assemble from those sources the actual shape of an actual life. The coal work, the Paris years, the character that comes through the letters, direct, warm with friends, passionately engaged with science as an intellectual project, and not merely as a means to a career, a person who loved France and mountains, and the kind of argument that sharpens thinking rather than the kind that merely establishes hierarchy. The biography put the science back. It gave the coal work space. It gave the Paris years their proper weight. It gave the virus research at Birkbeck the attention that the standard account, which ends with the photograph and the missed Nobel, had not given it. It rendered the injustice honestly, with the uncertainty intact, without the vocabulary of conspiracy. And it made the case, through accumulation rather than argument, that the most cited thing about Rosalind Franklin was not the most interesting thing. Her name is now on things. Rosalind Franklin University of Medicine and Science was established in 2004, a medical and health sciences institution in North Chicago, Illinois. The name is an institutional act of belated recognition. And it is one of those recognitions that is so much larger in scale than the original slight that the mathematics of restitution no longer apply. You cannot compensate a person who died at 37 by naming a building or a university after her. But you can signal to every student who enters something about who counts as a scientist. And then there is the rover. The European Space Agency named its ExoMars rover, which was in development during the 2010s, the Rosalind Franklin. The name was formally announced in 2019. The rover carries a drill and a laboratory and the capacity to look for signs of past or present life in the soil and rock of another planet. It was designed to move across a surface that no human has touched, examining material that has been unexamined for billions of years, looking for structures that might indicate biology. Her name is on a machine moving across Mars, looking for the evidence of life. She spent her working life learning to read the structural signatures of living matter, coal and carbon and DNA and virus, from the patterns that high-energy radiation leaves on photographic plates when it passes through a specimen and bends. She learned to see shapes that were too small to see directly, shapes hidden inside substances that looked homogeneous and undifferentiated to the naked eye. The X-ray cross on the photographic plate that became photograph 51 was a pattern, an encoding of a structure, a way of seeing what could not be seen directly. The rover on Mars is doing something not entirely different. It is looking for patterns in rock and soil that might encode the past presence of biology. It is looking at material that does not obviously reveal what it contains, and using instruments to read what is hidden inside. The methodology is not the same, but the impulse, the belief that the evidence is there, in the material, and that the right instrument and the right patients can read it, is the same impulse that governed every hour she spent in a dark room waiting for an exposure to finish. She would not have made the connection herself, probably. She was too precise for that kind of analogy. But the people who named the rover made it, and they were right to do so. What is the shape of this life, held at a sufficient distance to see it whole? She was born in Notting Hill in 1920 to a family that expected achievement and defined achievement in particular ways: law, banking, social reform. And she set those definitions aside at 15 or so, when she understood that what she wanted was to know how the physical world was structured. She entered Cambridge in 1938 and did the work of a degree without receiving the credential of one, because women at Cambridge did not receive full degrees until 1948, which is its own quiet institutional fact, unremarkable to the era and remarkable to look back at. She spent years studying coal, which most people do not think of as a scientific problem, but which is a problem in physical chemistry of considerable subtlety, and she solved parts of it that had not been solved before and published work that researchers in materials science still cite. She went to Paris and learned a technique from a man named Merong and spent 3 years in a city she loved. becoming expert in reading imperfect matter, not the clean crystals that gave up their secrets easily, but the amorphous and the disordered, the substances that diffracted unclearly and required interpretation. She brought that expertise to King's College London and applied it, with Raymond Gosling, to a molecule whose structure no one had determined. She separated that molecule into its two distinct forms. She controlled the conditions under which she imaged it with a precision that no one else had managed at that resolution. She produced a photograph after nearly 100 hours of accumulated exposure that showed the helical signature with a clarity that made a visiting scientist's pulse race. She extracted from the A form of the same molecule a set of measurements that included the symmetry of the unit cell, and those measurements contained, for anyone who could read them, the key geometric fact about how the two chains of the molecule were oriented relative to each other. Those measurements moved to Cambridge without her knowledge. The photograph was shown in Cambridge without her knowledge. The model built in Cambridge used both. She published, in the same issue of Nature as the model, X-ray data that was presented as confirmation of a Cambridge idea. And she left King's College the same year on terms that required her to leave the problem behind. And she did. She went to Birkbeck. She took up the tobacco mosaic virus. She spent 4 years building a precise and detailed structural account of a virus that everyone had assumed was solid, proving it was hollow, locating the runner at a measured distance from the central axis, describing the geometry of the protein subunits in a language that could be tested and reproduced. She built a model of that structure for the Brussels World's Fair in the last months before the cancer took her. She died at 37. 4 years later, the Nobel Prize that could not reach her went to 3 men, one of whom had built the model that was built on her data. In 1968, one of those men wrote a book that called her Rosie and described her as someone who could not see what was in front of her. In 2002, a biographer named Brenda Maddox wrote the corrective. Now her name is on a university and on a rover crossing another planet. The wrong done to her is real. The photograph moved without her. The report travelled to Cambridge without her participation or knowledge. The prize went to men, and 4 years earlier than it might have, because she died at 37 of a disease whose cause remains genuinely uncertain. To deny any of this would be dishonest. These things happened. But the wrong is not her measure. She had already done first-rate work before the photograph was made. She did more first-rate work after it. The coal research and the Paris years and the virus structures and the young scientist Aaron Klug, who sat at her elbow at Birkbeck and carried the methods forward into work that earned a Nobel of its own in 1982, these are not footnotes to the injustice. The injustice is a chapter in a life that was larger than it. The framing that reduces her to a wronged woman, to the person the photograph was taken from, is not precisely the same wrong that was done to her at King's, but it rhymes with it. At King's, her contribution was positioned as confirmation of someone else's insight. In the popular account, her life is positioned as confirmation of someone else's moral failure. In both cases, she disappears into her relation to other people's stories. She had her own story. It ran from a coal laboratory near Kingston upon Thames in 1940 through the back streets of Paris and into a dark room at King's College and then into a laboratory at Birkbeck, where a hollow virus gave up its geometry to a woman who had spent her whole working life learning to read what substances hid inside themselves. She was 37 years old. The work was not finished. The rover moves across the Martian surface in silence, the way that good work tends to move, without announcement, without ceremony, looking at the rock and the soil and the ancient structures that might be there, reading what is hidden. Her name is on it. The passages between what she knew and what remained to be known are still open. The earth is quiet. The long exposures that filled her working life are done, and the images have been developed, and what they showed has been absorbed into the body of things that human beings understand about the physical world. She gave the world that, not the injustice, the science. If this kind of slow journey helps you find your way to sleep, there are more stories here of the same careful kind, waiting for whenever you want them. And if you feel moved to share where in the world you are listening from tonight, I would genuinely like to know. The comments are there, and I read them. You have done enough for one night. Put down whatever remains of the day. You're moored safe in the sleepy harbour now. Drift off,